Yes.
So yeah, we're really lucky to have Zack with us today. He's from the Turing Institute. He's a research fellow there and also at the University of Cambridge. He's looking at a lot of physics-based applications to machine learning. So, yeah.
Thank you very much. Thanks, Naomi, and thanks to Maria for the invite. I'm really happy to be here. So as Naomi said, I'm from the Turing Institute and also a research fellow at the University of Cambridge. Just to introduce the Turing Institute, this is UK's National Institute for Data Science and AI, and it's currently housed in the British Library in London on Euston Road. And we do have a number of affiliations and links and partnerships with a variety of universities around the UK, and that even includes University of Leeds. So the work I'll present today was done in the last year, the previous year, and it was done across University of Cambridge and the Turing Institute, and that is with my previous group called the Energy Efficiencies Initiative. So the focus of this group was to build various types of models for energy forecasting across different scales, from city scales down to component and to building component scale. And this was led by Professor Xuereb. So just to start with, the methodology and the approach I'm talking about today is, I like to think of it as applied to dynamical systems in general, but eventually I'll show that I'll show a specific application on energy, because of course I was working with a group that was doing that. But I wanted to communicate that this methodology hopefully can be seen also from a much wider perspective. So in general, if we were to take a snapshot, there are we can categorize dynamical systems, rather models for dynamical systems in three areas. That is physics-based, also known as white box models, and these are derived from governing laws. There's data-driven models that are purely built from data, and there's also hybrid models that benefit from the two. So their structure, they have some form of structure that is inferred from mechanistic physics, and while their parameters are learned from data. So, but as you well know, data-driven models have taken have become quite popular, especially for time series forecasting, and that is time series forecasting for dynamical systems across any engineering application. And they're very popular because they're very good at extracting spatiotemporal structures from data without requiring much mechanistic understanding of the phenomenon. However, the caveat is that their robust generalization depends heavily on a large amount of data, and which is not always guaranteed in realistic situations, and might not also be feasible to collect. And also, the structure is not interpretable, so they have no correspondence. The structure of the model has no physical correspondence with any laws of physics or any form of mechanistic model. And these are reasons that inhibit their use in the real world. So real systems, like modeling real systems in the engineering world, really requires a bit of both, a bit of physics and a bit of data, and that is to gain to maintain interpretability in these models, but also models that don't need too much data to generalize robustly. And this is what the applied engineering world needs, and I like to identify these kind of criteria that we need to develop a new machine learning that is catered more for engineering, where again our models, machine learning that can generalize without depending on a large amount of data, and one that holds interpretability. And so the idea of fusing physics and laws of physics and data in the form of physics enhanced machine learning or physics informed machine learning could be a way to go about this. And so the project I'll share with you today focuses mostly on the generalization aspect, although it fits within this umbrella of also hopefully going towards also maintaining interpretability. And the goal here is to generalize in time and across domains. And the application, I repeat, is focusing on building energy modeling and forecasting, specifically with regards to building components. And this is very much to show a proof of concept, hence the simplicity maybe of the case study that I'll be showing. So in this approach, we couple reduced order physics-based models, which are very popular in energy building community, with domain adaptation, which is a kind of transfer learning approach. And the goal here is to forecast ahead of time given some observed data. So in one of the important things to consider when trying to incorporate physics in machine learning is how to represent knowledge. In this case, how to represent the physics that we know quite well. And so we want to leverage what already exists in the community, in this case, energy community, and that is these what are known as lumped parameter models or low rank models. Essentially, they are just low reduced order physics-based models where using a resistance capacitance analogy, you can represent the principal energy fluxes, the principal phenomenon that are occurring in, let's say, this thermal zone, which is this simplistic room here. And you could represent this on the right-hand side with what is known as an RC model in short, where the capacitors represent thermal capacity and the resistors represent some thermal exchange between the capacitors. Now, these are heavily used to model various scales in the energy community, from buildings, from complex thermal zones, down to even building components such as this wall, and even have labels such as 3R2C, which represents 3 resistors, 2 capacitors, because they have been proven in literature to be really reliable even in control set scenarios as a kind of predictor. Even though it's approximating the dynamics of the observed system, it is still very reliable. So we use this whenever we want to leverage this information and this structure in this sort of framework for machine learning. Now, we know very much, we already know how these systems operate and how they behave through differential equations that are very well known. And in this case, they are derived from the general heat balance equations. And these equations are used to inform the parameters of these RC models on the left. Again, these are very well known equations and laws of physics that we want to leverage. So these models could either be formed from data, but in this case, we want to leverage purely physics. So the parameters of the model are derived directly from these very simplistic equations. We can also represent these RC networks as in a more standardized fashion, and that is using state space models. Essentially, they're used interchangeably, but for clarity's sake here, I'm showing sort of a progression. So essentially state space models, in this case linear state space models, are composed of 2 main equations. One is the top equation is related to the state equation, to the states. So that is understanding the relationship between the states of the system and the influence also of some external forcings, which in this case we're considering as the external temperature. So if you look at the wall on the left, we have this wall cross section. Tx is the external temperature, coming from the weather. So we could think of it as either a control variable or as some form of noise. And what we care about, what we want to model, what we're interested in is the dynamics through the wall. So that is to capture the dynamics of the wall, and that is between Tx2, which is the temperature on the outside of the wall, and Tx1, which is the temperature on the inside surface of the wall, and that their interaction with the temperature inside the room. So we can model that as a state space model, as I said here, where the external temperature is now a control variable, and the states, which are the surface temperatures, are now the states of the system. And what's important to note here is that the A matrix is where all the magic happens. Essentially, it contains the knowledge of how the heat is transferred from the outside to the inside through the wall. And without getting into too much detail, I'd like to visualize this. So once we can solve this system of equations, that would give us time series. And to visualize better, the time series indicates the the temperature of the surface of the wall on the inside of, okay, so that's after conduction has happened. And you can see obviously that the Tx1 is more dampened than Tx2 because of course there was conduction that was happening through the wall. So now this is how we usually visualize time series data through in the as a function of time in observed space. But if we plot them against each other, we can start to look at certain geometrical aspects. And here we're looking at the system in state space. So the system in a state space visualizes the trajectory of this entire system state through time. Now, if we decouple the noise, which is the external forcing on that system, from the actual conduction that's happening, which is the physics we care about in this particular case, we can see that we are left with a very smooth trajectory in the state space. And if we focus on that, so that's basically only looking at the dynamics of A. If we focus on that, we have this trajectory that describes the temporal evolution of the temperature states towards thermal equilibrium, which is a sort of steady state situation. And it can reach thermal equilibrium because it's not being forced by the weather, by the external temperature. Now, just to give more picture, if you notice in this particular case, it is showing us how the internal temperature, the internal temperature reaches steady state at a much slower rate than, of course, the external temperature, and that's because of conduction. Now, this trajectory is governed by a state space field, by a vector field, and that vector field is governed by the eigenvectors and the eigenvalues of the A matrix of that system. So that A matrix contains all the information you need to explain the governing system, which means that given that field, now you can drop a metaphorical ball in that field, and it would always reach, it would trace a path to states to the thermal equilibrium. And in a snapshot here, we have a geometrical representation of that system. So we've gone from looking at the physics of this simple wall as an RC network to visualizing it as the same system and its governing behavior as as geometrically, essentially. And this is very much related to manifolds, but I won't get into that now. This is essentially a phase space, the geometry of the phase space. And it's this geometry that I want to. Yes.
Sorry, can I because I missed one part. So if you go in the previous slide when you have the equation. So for example, here your independent variable is x. So what is x?
Sorry, so x is the state. So the x of t is the updated state. So so the tx1, tx2 is the state of the system at time step, the previous time step, and x of t is the following time step. So it's the tx1, tx2. I'm sorry, I should have noted that as more clearly.
So x is the combination of the external temperature, internal temperature, and the temperature at the walls.
That's correct. But now because we're visualizing the state space without the forcing, without the B, right? It's simply the updated time step, the updated state without the forcing. So it's essentially the position in the state space along the trajectory.
Okay. And why does it depend on the temperature and not on the previous position?
Sorry.
And why don't you have an x on t-1 on the right hand side of the equation?
So the A matrix is when multiplied by the states, by the states of the time step, is updating the states to the new time step. So that's what it is.
Okay. Nice. Thanks.
Oh, that's fine, right?
That's fine.
Okay. Okay. So the goal here is to find a new way of representing physics for, again, machine learning, for this fusion of physics and machine learning. And what really fascinated me, so mind you, my background is I'm an architect, and geometry was sort of our tool. And I did not know much about physics and how you could represent physical systems as geometrically. And so this led me slightly into the field of differential geometry, and it fascinated me that the fact that you can actually, understand and represent governing behavior geometrically. So if we look at a different system, which is okay, it's a slightly thicker wall, but essentially it's a different system, and we do the same, visualize the state space geometry, we can see that they're different, but they're also very similar. So this begs sort of a question which I will ask in the next slide. This is simply showing more wall thicknesses, varying the wall thickness and how that geometry changes. And you can see that there is an obvious kind of transformation happening there. There's a rotation and some scaling. And also the speed at which they're reaching this state space, the equilibrium point, is varying according to the thickness. As you can see, the thicker ones take much more time to reach the equilibrium point. So, just 1 second. So we can actually also infer these geometries from observed data. So by simply using methods like unsupervised reduced order modeling, SVD based, so POD or DMD, and because these methods give us the eigenvectors and eigenvalues of that system. Now, obviously, those eigenvectors and eigenvalues will not be coming from like continuous space. They will continuous time. They're going to be only describe a part of the physics of that system, and part of the ultimate goal, which is beyond this research project today, is to find ways of discovering the complete governing behavior from data by leveraging physics that we already know. So in this case, what we can see is that once we can extract these from data, we can infer them from data in the same manner. If we compare the geometries, we can start to see that we can maybe find transformations between physics and data. And that is purely through their state spaces. And hence this slide, where we have a source and a target, and we want to leverage the source that is coming from continuous time physics to forecast better in the target space, and which is the data, observed data. So this led me to, this sounded very familiar, and it sounded very much like domain adaptation, which is a method that already exists widely in the sort of computer vision community, and they use it mostly to leverage labeled data that they have to predict for unlabeled data for very similar problems. In this case, it's different angles, sorry, different camera views. And it's very much a very similar problem to what I'm dealing with here. And so how this works generally is you infer the eigenvectors from each of your source and target, which in this case, in this problem, it's images, and that is using PCA. And then the goal is to find a geometric transformation that transforms the coordinate base of the source closer towards the target base, and then using that transformation to transform the labels into the new space. So instead, in this approach, what I want to do is, rather than have images as a source, I have physics. And the cool thing is that we have eigenvectors, and they're not coming from PCA or from data, but they actually mean something. They're coming from the physics that I just explained, and they describe the governing system, and that's really, really cool. So the fact that we can leverage that already, because we can extract the eigenvectors from the target data, as I've explained earlier, and find the transformation in a similar manner. And then, so mind you, I use a method here called procrustes analysis, not very important, but it's just one way of finding geometry transformation between vector bases. It's quite an old school analysis method. So the goal then is, once we have this transformation, is to project the source and the target data onto the respective, now called subspaces. And so as you notice, the goal here is to forecast time steps ahead in the observed in the target domain using the source model. So because the source physics, the state space model is sort of computationally cheap, and I can generate as much like I can transform that data into the new aligned space, which will result in a forecast. So essentially, this is the outline of the method, and what essentially the procrustes-based method is an SVD. So it gives us, what it gives us is a kind of not just a transformation, but it gives us rotation, scaling, and also sort of a skewing factor. And then these are applied to, these are used, of course, to transform the source generated data from the physics into the data domain. So I'll just show two examples. In the first example, I'll show how we can leverage physics for calibration purposes. So I have a physics-based model, and I have got some data in this case, of course, I'm not dealing with observed data from an actual wall. I'm using numerical data that I generated using a finite element solver as a kind of high fidelity, as an emulator of the real data that we would deal with. And so in the first exercise, I want to show how this transformation, how we could apply this approach to leverage the physics of a 0.2 meter wall to nudge it closer to the actual data. And in a second, for a wall of the same thickness. And in the second approach, I want to show how we can use even physics from a different problem, but related domain, to do the same. And because the framework could be used in both ways. So in this first example, the model, the physics-based model was already quite close to the actual to the observed data in the target space. But with the transformation, we're able to nudge it even closer. So the dotted line is the state space from physics. The solid line is from the finite element analysis, and the red line is what was transformed from the source to the target. So the training happened on the first in the white patch, and the right hand side is the forecast. Sorry. So onto the second example, we can see that now we're leveraging the physics description, the state-space model of a wall of 0.6 meters thickness to forecast in a domain for a wall that is of a different material. So it's of a different thickness. It's 0.2 meters. And so as you can see, the 0.6 meter wall, which is the much more dampened time series because of the thickness, has been transformed. The transformation has been learned and then applied to forecast quite well on the right hand side. And this is a similar case, but for changes in material. So we're transferring from a wall of different thickness and different material to another wall of different thickness and material. And in this case, I want to show that given that this is, oops. What happened there? Oh, yes, of course it has. Excuse me, my PowerPoint presentation has seemed to have crashed. Apologies. Okay. This is not the day for now. Oops. Okay, so what I wanted to show here was that given that the data we're dealing with is somewhat not noisy, right? It's coming from finite element analysis. We added some noise to the observed data, so that's the data we want to forecast with, and because the reduced order modeling method acts like a filter from a spectral decomposition perspective, it's able to filter out that before learning the transformation, which then obviously helps to learn the correct transformation and forecast accordingly.
Zack, may I ask a question? So
Yes.
Now, for example, you have the source time series as the smooth one, and then you do POD analysis on that, on the smooth time series at the 0.8.
POD happens on the smooth one is the physics. So there's no POD happening there. The POD happens only on the data to obtain the eigenvectors to be aligned with. So I can go back to the slide where I explain the methodology if you want.
Mm-hmm.
So on the left hand side is the source, which is coming from physics. There's no data involved at all there. On the right hand side, so in the case of the example that I've just explained, the smooth one would come from the physics side.
Mm-hmm.
And
so you know the eigenvectors there.
Exactly, and those eigenvectors are they're governing the entire system. Whereas the POD, we apply only on the data, on the observed data for the target, which in that example is the noisy signal.
So there is no deep learning here.
No, in this particular situation, there is no deep learning. This is purely this is literally the early stages of a proof of concept that's going to hopefully lead to go towards deep learning. But the goal here is to show that we can think about dynamical systems purely geometrically and leverage that structure for ultimately deep learning. Yes, deep learning applied in, so a lot of the caveats that I find with applying, there are still physics and machine learning methods using deep learning that don't address the caveats I mentioned earlier, which is things like interpretability. We do maintain some structure, but you still end up with a components and terms that are black boxes. Which, so I like to push using the most classic methods until the very end, and then only work with deep learning when we need to work with deep learning.
Okay. Now I was just about thinking about transfer learning. So in this case, the transfer learning is the rotation of the
it's purely geometric. Obviously, now in the next steps, when we start to deal with super nonlinear systems, deep learning will definitely come in to help us find the mappings that right now we can find, because we are dealing with mostly they're weakly nonlinear systems. But when you deal with highly nonlinear systems, then yes, you're going to have to just explore more the deep learning route. But we can have a discussion afterwards, and actually I'd like to hear all of your opinions on this, because I think it's a really pressing topic on how do we use deep learning but maintain, you know, this interpretability that is so important in the applied world.
Okay, thanks.
Thank you. So this work was recently published in the Data-Centric Engineering journal, and in the current next steps, this is going to provoke a lot of questions that are again geometry based and maybe at a more fundamental level. And so one of them is that when we deal with observed data, when we collect data, we don't have the smooth manifolds that we see on the left-hand side, but rather the time step resolution, which is something we might not always be able to control in the real world when you're sensing structures or sensing environments or measuring data. You might not always have access to like high resolution time steps. So you end up with state spaces that look like this on the right-hand side. And so one of the questions is, can we leverage, can we introduce, even if deep learning is involved here, can we introduce inductive biases that leverage this knowledge that we have? So it would be like the smoothness of the physics trajectory that we know and we can describe, and then leverage that in the learning process to recover smoother geometries in the target domain. And that might mean that we could get closer to things like learning, you know, the complete picture of the physics of that system. And that's sort of, for me, that's a really provoking direction, because a lot of the models we build, a lot of the hype on machine learning and deep learning in the engineering world, I feel isn't validated, isn't stretched to the limit, because a lot of these models don't generalize values because they don't only learn a small piece of the picture. Even in physics and machine learning, we need to develop metrics and tools to measure how complete is my model, and that is what is the distance from, you know, the governing system, the governing geometry, perhaps. I believe geometric approaches could be an interesting direction to answer these questions, because we have all the methods from differential geometry. We can represent dynamical systems and dynamical systems from data using geometry, and we could use these differential geometry tools to find ways of measuring these things. So, oops. Yes, I'll go through this. And one direction I'm taking now is looking at manifolds and looking at, rather than looking at individual systems, we can start to think about population of systems and how these are related on manifolds. And if we're able to, again, leverage this idea of the geometry of physics that we know, we can start to model manifolds that relate systems, ultimately can be interpolated, potentially parametrically, and would help us to model unobserved systems efficiently by leveraging, again, its neighboring systems. I won't say too much because of course this is just initiated. There's not much to say at this point, but it's a really cool intersection that I think I would be excited if anybody in this room was interested in and would like to have a chat about. So before ending, though, I'd like to also talk about what we do at the Turing. And so this research forms part of the program at the Turing called the data-centric engineering. And essentially, it's the DCE, as we call it, is sort of a program that brings together academics and industry partners from around the UK, and that sort of try to address grand challenges across the UK. And some of the projects we have some projects on digital twins in civil engineering. So, for example, here this was a project that involved building a digital twin for the world's first 3D printed bridge. So this bridge was monitored with sensors, and there was a digital interface that would help practitioners analyze, monitor the structural behavior of the bridge. I'll just run through these. So there is a digital twins in aeronautics, and this helps again practitioners in the field to optimize and predict asset performance. There is another more recent digital twin which I was lucky enough to work on for the last year, which was a digital twin for an urban agriculture farm, which is situated 30 meters below ground in in an unused London underground tunnel, and they grew microgreens. And we had this digital twin. Besides the interface, of course, we had forecasting models based on sensors and real-time data streams. And my last role was actually using methods like dynamic mode decomposition to extract and to understand the spectral structure of the behavior of the farm, and use that to build simplistic and more compact models. Unfortunately, there's not enough time for me to show it today because I was going to show them, but I don't want to keep you too long. If we were to focus more on physics and machine learning, there's other work going on which involves predicting extreme and rare events, such as weather. And in this particular case, this research was by Luca Magri, who I'm not sure you're familiar with, from the Imperial College. And it looks at physics-constrained data-driven prediction by leveraging reservoir computing and recurrent neural networks. And also more work on sourcing location inference, and that is identifying unobserved sensor locations, so predicting for locations that have not been observed using multi-level models. Right, and lastly, I would like to say thank you, of course, for everyone for joining, but also I'm co-editing a journal with Alice Xuereb from TU Delft with a focus on physics and machine learning targeted to applied solid mechanics. So if any of you are working in this field or have any friends or colleagues that are, I would really appreciate if you could encourage them to submit to this special issue. Thank you.
So I suppose first, is there any questions in the room or online?
Maybe just comment on like an amount of data and generalization. But if you have more data, you get more realistic prediction or comprehension of how well you generalize.
This is like, you mean like in a normal data-driven approach?
No, but I mean just like when you're talking about just the amount of data to train the model, but also to get a good complete picture of how well the model generalizes, you also require large amounts of data.
So yes, interesting point. So my view is, as a baseline, the idea of throwing data at a model for generalizing is, I feel it's not about the amount of data, it's about the representativeness of the dynamics in the data, which is hard to obviously find and know. Yes. So we have no choice but to throw data at it. But the idea, in my view, is the idea by leveraging the physics, because there are complete pictures, we don't have to deal with throwing in so much data. Yes, we need to develop metrics on how to see we need some form of metric how far away the data is from complete picture. That's where the work has to go in. Because if we have that, then we can really get complete. We can literally see how much more we need to complete or where we need to complete based on the source physics that we have. But yeah.
And maybe also how much background research exists in this kind of domain where you domain adaptation, shared data representation, or shared geometry. So I would reckon that that's kind of the most early approaches for domain adaptation.
So can you repeat the last part of the question?
Like the domain adaptation
Yes.
in this geometry or kind of shared data representation. Yep. I guess this is the kind of most established techniques for domain adaptation.
So the domain adaptation, so this particular case, there are many types of domain adaptation. This is subspace-based domain adaptation. So it's purely
the idea of
yeah, but the idea, yeah,
shared.
Yeah, it is. There is a lot of work on Geometrical, yes, for sure. But they take I've seen domain adaptation in that area, but it takes the form of still networks-based. It's more oriented towards deep learning, and I think that's leading to another area called geometric deep learning, which again explores differential geometries in a deep learning setting, and that's very exciting as well, because you can improve a lot of the things I mentioned, a lot of the caveats I mentioned, purely through sort of geometric operations at a more, I think it's at a more, it's at a network level, not in the way I've been doing it here. But yeah, it does exist, yeah. I mean, I have not explored that field too much, though. Also, my knowledge on differential geometry is so backwards, but this is probably a scary thing to do. Right. I also realized I thought I would actually take much longer, but I was quite quick.
If there's no more questions, I think giving a big thanks to Zack.
Thank you. Thanks for having me.
Yes.
Thank you very much.
It was really nice. Thanks a lot for joining, for coming from London, and maybe we can discuss later on some opportunities for collaboration, for having indeed like this a joint seminar.
Absolutely, absolutely. Very keen.
Because what I was just curious. Wait, I'm gonna stop the recording. I was actually curious.